So let's see if we can explain this by maybe doing a small signal analysis of our circuit, because we kind of know what the values of the voltages and currents are to see if we could approximate what's going on. Again, RO is a pretty large resistor, so we could just neglect that in our AC model. And we could use the GMV pi model, or we could go back to what we did for a lot of 302, which is a AC beta times the AC current. It'll turn out in this particular stage analysis, this will be a little bit less work, although you'll get the same answer no matter which model you use. So here I've got node voltage 8, which is the base lead of transistor 11. And again, if we're operating our Darlington pair, the top half is on or the bottom half is on. Let's assume that the signal is slightly positive, and so the top half is on in the active region, and likewise over here. So this is going to be Q11, which is the NPN, and here is the PNP transistor, Q13. Our battery looks like a short for AC. We've got a large coupling capacitor here of 470 microfarads. It looks like a short circuit. And we have our 100 ohm resistor here. Again, I'll say everything we can on the schematic. Here's IB11, here's IB13, and that's also going to be equal to the collector current of this transistor, which is the beta, AC beta times the base current. You can also stick that back over here too, that IB13 is equal to beta naught 11. This is again the AC beta times IB11. And the current coming down here is going to be IB11 plus beta naught 11 times IB11, so it's beta naught 11 plus 1 times IB11. And then what I've got here is beta naught 11 times beta naught 13. Now again, these are both pretty large numbers, again on the order of 100 or so. So the sum of this with this is approximately just this. So the node voltage here then would equal this drop, which is IB11, R pi 11, and then 100 times this current. And then lastly, the drop across here would be R sub L times beta naught 13 and beta naught 11 times IB11. Again, this is on the order of 100, so we kind of could throw the 1 away that's here. And so we could pull out an IB11 from each term. We'd have R pi 11, 100 times beta naught 11, and then R sub L times beta naught 11 plus beta naught 13. Could also solve for V out over V sub 8, because we have V out here as beta naught 13 times beta naught 11 times IB11. It's this term right here. And then we could divide that by our V sub 8, node voltage 8, throwing away the 1, which is right here. And then the IB11s drop out. And so we've got this numerator term, which is pretty large, and a similar large term here. And what we were approximating before is that roughly this was a gain of 1, but actually these two terms are here. The R pi probably won't be much of an effect, but the 100 times the resistor of 100 ohms being multiplied by the AC beta of transistor 11 will actually account for the error that we're seeing. Now, what are the values of beta naught 11 and 13 and so on in R pi 1? Well, you can go back and run a SPICE simulation and get the biasing points. But here's where we're going to run into a rather interesting problem. If you run SPICE and ask for the operating point, it sets the AC source as equal to 0. And what that's going to do is it's actually going to bias the transistor amplifier kind of in that region where it was in off. Both the top and the bottom part of the Darlington pair are actually off. And you can see that actually from the collector currents for 11, 12, 13, and 14 that they're sitting at extremely small values for the collector current. We need things to be in the milliamp range before we're going to have some voltage across the speaker. This is one of the dilemmas of dealing with simulations of power amplifiers, is that when you try to do an AC analysis, you're going to get a rather strange result because you're really biasing the amplifier here, and the gain will be extremely small and be way off from what you expect it to see. And so I figured a little trick, still be able to do some calculations. So if I were to take a look at not an AC analysis or phasor analysis, but actually look at a large signal analysis and in the time domain, and maybe look at when our currents are maybe at their peak value, then we could read off collector currents of transistors and then calculate the values of DC beta and then the value of R pi. And the DC and the AC beta are pretty close to each other. Not exact as we saw in 302, but pretty close to each other. Let's do that. Here is the collector in the base of Q11, and you can see I marked the values at the peak. And likewise for Q13, this is a PNP transistor, so the collector current is defined actually going into the collector, but in reality it's coming out. The same is true for the base current, and so put the negative of it there. So if we use the value of the base current at its peak, we're calculating the small signal model in one instance in time. So we're looking at a part of the waveform of the top transistors when they are actually biased in the active region. Okay, so using the value of 5.9 microamps above, I get about 4.4K for our pi. Now again, if you look at the operating point on the previous page, you'll see that it's quite different than that number. Because again, it was biased at the wrong place. And we're looking at, in some sense, dynamically one point on the curve. This is a trick I've used in lots of power amplifiers to kind of calculate some AC parameters and the like, even though this is, again, a very nonlinear type curve. But at a point, we can approximate it with a linear model. And then the ratio of the collector to the base current is 132. So that's roughly going to be our AC beta. And for transistor 13, having a much larger value of current, we're looking at an R pi of only about 33 ohms. And then the ratio of the collector to the base current is about 112. So again, these are large numbers, but we could use this point on the curve to get an idea of what those are. So now I can go back to the formula we just had a few pages earlier, and now I can put in the values for R sub L, for beta naught 11, and beta naught 13, the value of R pi, and then here's our beta again, and then our R sub L, and then our two values of beta. And so sure enough, we can predict that the gain isn't 1, but actually a little bit less than 1. So using that calculation, I get around 0.87. Now remember, we measured that about 0.778. So that's sort of what's accounting for the little bit of loss in the amplifier. Okay, lastly, I'd like to predict roughly the 3 dB bandwidth. The bandwidth of the amplifier will actually determine how much noise we hear in the output. So what we've got is this Darlington pair circuit with half of it on, half of it off. And so I just drew that as a box here. And then we've got the preamplifier, and there was a 3.3K resistor, battery back to ground, but we're going to short that because for AC it looks like a short. And then there's a 0.001 microfarad capacitor. And the diode, you could calculate actually A to V sub T over I sub D as we did in 302 to predict the value of resistance. We could also use page 17. There's a table with the biasing. Because this stage was biased not in cutoff but actually on. So in the biasing currents for the diode were actually, if you look back on page 17, was 1.17 milliamps. And again, we approximated 1.2. So we got a rough handle as to where we thought the numbers might be going. Okay, then we have our 8 ohm load, and then there's a feedback resistor back through here. And the question is, what is that doing? Well, since the output is around 100 times bigger than the input, then the voltage across this resistor is going to be this node voltage minus this node voltage, but that's roughly the same as V out. So what that's really saying is that this is really in parallel with this. So this resistor has no effect, or very little effect for the AC analysis. It was just used to bring the biasing for this transistor. Now I want to estimate node voltage 8, and of course the current that's going to be flowing in here is the same as in here. And again, I'm going to throw away R0, because what's in parallel with this is something much, much less than 100K. So we're just going to throw that R0 away. So the GM10 VPi10 is flowing through here, and flowing in this parallel combination, and then that's in parallel with the input impedance of the next stage. And again, we predicted that, I get a chance to point out here, with the formula we had just derived, and it's about 135K. Here's the R pi, 100 times beta naught, I think was 11, and then the product of the two betas. So pretty much you could neglect the input impedance of this, and that was part of adding that Darlington stage, is that this little loop determines the gain of the circuit, and that's what we were approximating before, with a gain of 127, or the negative because of the phase inversion of this. So what you really got is this GM10 VPi10 flowing in this parallel combination. So you could write that as 1 over the conductance or admittance, and that would just be 1 over 3.3K, and then a capacitance of 1 nanofarad, so the admittance of that just being S times C. So I can multiply through here by 1 over 1 nano, that give me 1 over 1 nano here, and then 1 over 1 nano and 3.3K. This is really the form of a low-pass filter. Using our forms, we could predict the response that we have. Actually, this should be a form 5. And so here is a denominator with a single pole, and so the corner frequency would just be 1 over 2 pi divided into that frequency. And you get about 48.2 kilohertz. So to predict the overall gain of this amplifier before we put in the actual circuitry, we approximated to be about 127 in magnitude. Found that the output stage had a little bit less than a gain of 1, and so that brought the gain down to about a gain of 100 or so. We're going to measure this and compare it to some of our calculations. And then an overall bandwidth of about 48 kilohertz, so a little bit wider than the audio band, and we're going to actually measure the bandwidth as we do the experiment. Let's see if this actually works. Again, we can't do a small signal analysis because of the biasing problems that they'll find the small signal model when the amplifier is actually cut off, and so you get some really strange bandwidth calculations. Very confusing when you're doing splice simulation, but you have to understand what the program is doing. When you ask for the operating point, it sets all of the AC signals equal to 0 and then finds where you're sitting. And for this kind of an amplifier, when you have no input, you're basically sitting in cutoff, which is what you want for a power amplifier. You want to consume power when there's no AC input. So let's again do time domain, but let me go back and change the frequency in the simulation file that we had seen a little bit earlier. It's on page 13. And I'm going to just change the frequency to 50 kilohertz from, I think it was 1 kilohertz. Again, you can measure the output. It's about 1.12 volts peak to peak. A little more distortion we're seeing now as we're going up in frequency. And then the voltage coming into the preamp is about 16 millivolts peak to peak. And if you take the ratio of those two, again, you can see the phase change between them. So there's your minus sign. Not exactly 90 degrees now, because we're really thinking or estimating that this would be the 3 dB point, which we would actually have a 45 degree change in phase angle. And if you measure that, it's probably pretty close. But the gain now turns out to be 70.4, and that's approximately 98 divided by the square root of 2. So we'd be down 3 dB from the mid-band gain. I had just run an operating point simulation. In fact, I did. I found that the 3 dB bandwidth was actually about 23 kilohertz. But in reality, I knew this couldn't be right because I had taken some measurements and found it was quite different than that. And that's why I kind of went back and showed this little trick. So again, let me just kind of summarize this. When you do a dot OP for an operating point to find the transistor models and where the AC parameters are, that's what's going to be done for an AC analysis. And so because this device amplifier is actually in cutoff when you have a 0 input, then you're going to have models built around the wrong regions. So by looking at a time domain response, you can take parts off of a curve, approximate in a neighborhood of what the gain's roughly doing, and you can see the overall effect of all this together. Again, as with any lab, the purpose of this is laid out usually in the lab experiment itself. And we're also covering concepts and laboratory techniques. So our purpose here is we're going to take a look at how an AM/FM radio works to get some ideas for the rest of our high-frequency topics in the course. A good way to do that is take a look at something where we're not dealing with all of the idiosyncrasies of the transmission lines. I picked an AM/FM radio because there's a lot of ideas in there that we're just going to build on. This also is a radio frequency application. We're also going to learn about how soldering and how to do some testing, at least on the audio portion of for this week's lab. And the concepts we just covered were AC and DC models of bipolar transistors. Again, a little bit of a review from 302. A complementary Darlington pair, which is new. Small signal bandwidth, and then efficiency. In lab, you'll see that we'll be taking a look at how to do soldering. We're going to try to do some troubleshooting to just check that we've not made any soldering mistakes by just doing some DC measurements. So using called static measurements, which are really DC, using a digital multimeter just to see if the biasing is coming out where we think it is, just as a check on our soldering. We're going to measure gain and bandwidth using our oscilloscope, and likewise use our power supplies to also calculate efficiency.